Hello, everybody. I hope you had a nice weekend after the homework turnout. So today we're going to continue with time-independent perturbation theory. In particular, we're going to study the degenerate case when we have degenerate energy levels. The remaining part, it's basically related to this and also to the viewpoint of looking at time-independent perturbation theory as some sort of iterative method. So probably today, I'm going to talk most about the degeneracy. Um, I think that gives enough time for the video to be digestible, both for you and for me. And possibly by the end of this week on Friday, I will upload um, the last video related to time-independent perturbation theory, in particular to the iterative method. So, okay, let's start. And let me share my screen. Okay, yeah. So again, the remaining things to talk about time-independent perturbation theory, it's basically the first order corrections to degenerate energy levels and the good wave functions, and non-degenerate time-independent perturbation theory as an iterative method. So, okay, why do we have to do a different treatment? Essentially, when we developed perturbation theory and we calculated the corrections to the second order energies and the wave functions to first order, we noticed that there was a term in the denominator related to energy differences. And so the problem is that in the case of degenerate energies, meaning that we have, say, at least two linearly independent Eigen States that have the same energy, the denominator will be zero. And so this blowing up of, say, the first order correction to the wave function or the second order correction to the energy brings into question if the method is well posed for that case. So we just need to modify the method slightly to handle the degenerate case. But it means that we have to recalculate things for the degenerate case, even for the first order corrections to the energy, which didn't seem to have the issue of the denominator zero. Because, loosely speaking, if the series expansion is blowing up, what is the validity of it in general? So we'll have to calculate things again. I will explain it clearly. And it's not a minor point or a moot point because many of the applications of perturbation theory involve degenerate states. So, well, it's important to consider this issue, and we'll start now. And basically, we will go first with a simple case and then to the more general case regarding the dimension of the degenerate eigenspace. So basically, you look at an energy level and you look for the dimensions of the, or the dimension of the eigenspace that has this energy eigenvalue. If we were in the non-degenerate case, basically the dimension would be 1. However, we are in the degenerate case, and so the dimension is either 2 or greater than 2. So the simplest case is to analyze degeneracy where the eigenspace, the degenerate subspace, is of dimension 2, which is twofold degeneracy. And yeah, again, let's say that for our energy value, the dimension of the eigenspace was 2, right? So basically, we can have, or we can define two orthonormal eigenvectors that span the subspace. We're going to call them phi 0a and phi 0b. They are both eigenvectors or eigenfunctions, sorry, of the Hamiltonian operator in the perturbed case with eigenvalue E naught, both for phi 0a and phi 0b. And they can be chosen orthogonally as they are linearly independent. So we'll assume that we have already chosen phi 0a and phi 0b as for this. And so let's say that we introduce a perturbation to the Hamiltonian, right? So what does a perturbation do? It slightly changes the eigenstates, that's true, but also the eigenvalues. So in this small perturbation case, the perturbation most probably will remove the degeneracy, meaning that it will change slightly the eigenfunctions, also slightly the eigenvalues, but it will make them different. And in the unperturbed case, they're equal. But when you add the perturbation, most probably they won't, unless coincidentally that's the case for the perturbation that you introduce. But that means, okay, that the perturbation breaks the degeneracy. And so still thinking of this lambda parameter that at the end of the day we make equal to 1, more of about that to come very soon. Um, let's say that we think that basically lambda goes from 0 to 1, right? So h prime is fixed, lambda is like you are switching it, right? And you're turning on the switch, it goes from 0 to 1. And so in the case lambda equal to 0, you're in the unperturbed case. And again, where the energies are the same for these two states. And then for lambda greater than 0 and less or equal to 1, you will break the degeneracy and you'll have two different energies. So if you think about it in the reverse way, meaning that you start with lambda equal to 1 and then decrease to the limit lambda um, approaching 0, uh, well, basically what you would have is um, so the two different energies with different eigenstate would become 1 at lambda equal to 0, right? So you most probably will go from different energies to the same energy for the case lambda equal to 0. And so the eigenstate that was before related to a higher energy will become a linear combination of our basis for the degenerate subspace, phi 0a and phi 0b. The one for the lower energy will have the same energy as the other, and it will also be an orthogonal linear combination uh, from lambda 0 to 1. Because, I mean, think about it this way. When we had lambda not equal to 0, the energy was different. So that means that because you have two different energies, the eigenfunctions cannot be linearly dependent, meaning that they cannot be proportional to one another. And so in that case, the states in the perturbed case were linearly independent, and you basically want to go to the limit case of lambda equal to 0, where you still retain the linearly independence. So for all the cases lambda not 0, you had linear independence, and you want to keep the good choice of so-called good states so that you retain the linear independence um, when you go to case lambda equal to 0. So, well, um, again, so what we have to do is to find the good and perturbed states, which are linear combinations of phi 0a and phi 0b, that are the limit of the true eigenstates for previously different energies as lambda approaches 0. And so that will help us perform the time-independent perturbation theory for the degenerate case. This, in principle, cannot be done exactly. But what we know is that this limit that we want to find, that we're going to call the good states and unperturbed, say in the unperturbed case with lambda equal to 0, they are linear combinations of phi 0a and phi 0b, right? And so we know that, okay, it will be a linear combination of the bases that we have. And well, we have a new Hamiltonian. So we want to solve the eigenvalue problem of Schrodinger equation with this new Hamiltonian, where again, we have the unperturbed Hamiltonian H naught plus lambda, which is a controlled parameter that we are, it's clear in this degenerate treatment that we're kind of like tuning or turning on and off, making it go from 0 to 1, times H prime, which is the perturbation Hamiltonian. Of course, at the end of the day, we'll make lambda equal to 1. Just wait for that at the very end. So that is H. And okay, we want to solve the eigenvalue problem, right? And we do the same treatment of perturbation theory, where we expand the energies in terms of corrections of different order in lambda. So the lowest order will be related to E naught, which are the unperturbed energies, and likewise for psi, the order 0 will be related to the unperturbed eigenfunctions. So we do a substitution as we did for the previous case. This is actually quite similar to what we did in the past in the last two lectures. So basically we focus on this expansion. Okay, on this side we have the energy expanded in terms of the parameter lambda and corrections times psi, likewise. So, excuse me, this is related to the ground state. This is the contribution of higher powers of lambda. Likewise, well, we know that H prime, or the term related to H prime, has an additional power in lambda coming from here. So this is the ground state term, or sorry, the ground, the 0 order in lambda term, sorry about that. And then higher powers in lambda. So matching the powers in lambda again gives us that we have the perturbed case, which we already know. So it's just a sanity check, no new information there. And if we go to equating powers on the same degree on lambda, we have again this balance, right? So at first order, we have H naught psi 1 plus H prime psi naught, again, because of this power lambda over here, equal to E naught psi 1 plus E1 psi naught. So we do the same trick of basically projecting onto the space that we want, which is we'll take inner product with respect to psi 0a, which is one of the two elements of our basis for the two-dimensional degenerate subspace. And if we do that, multiplying, okay, we'll have this times the first order correction, then, okay, the state we care about, our inner product with A prime times psi naught equal to psi 0a, inner product with E naught psi 1 plus psi 0a, inner product with E1 psi naught, right? So, okay, we can cancel some of the terms. Basically, if we apply the operator to psi a, remembering that we had this property, we will get this same term. So that goes out to cancel. And well, later on, what we remember is that psi naught, which is what we want to find, is basically a linear combination of the states psi 0a plus psi 0b with the coefficients alpha and beta. So we plug that in here. We basically use linearity on this side. Likewise for this other term. So be mindful that basically this term and this term are the ones we canceled due to the psi 0a being an unperturbed eigenfunction for H naught. And well, over here, what we can do is basically apply linearity in the sense that one of the terms will die out. And the reason it died out is because we're taking inner product with psi 0a. When we do the expansion, the E1 will come out as a scalar. And so the term related to psi 0b will die out. And so that's why we only keep the coefficient alpha in here when we take basically inner product with this. So basically this is constant came out, and then we apply inner product and orthonormality, and that's why we get only the coefficient alpha multiplied by E1. So, okay, so far so good. And now we're going to introduce a notation for the matrix elements of H prime in this degenerate subspace. And of course, the bases we're taking in the degenerate subspace are the wave functions by psi 0a, psi 0b. And so we define Wij as, well, inner product of psi 0I, uh, inner product with H prime of psi 0j. So H prime is sandwiched between the functions of the, in this case, two-dimensional um, basis. And the indexes, because of the notation that we use to denote them, I and j can be either A or B, right? So if we do that using this notation, we can re-express this equation. Okay, this would correspond, or this term, to WAA, of course, multiplied by alpha plus beta, and then you have WAB, of course, then equal to alpha A1. And you can do the same trick of basically projecting into the space that you care about, which means multiplying or taking inner product with respect to psi 0b, and you would have an equivalent equation of alpha WBA plus beta WBB equal to B E1. So you just have to basically take inner product of this equation with respect to psi 0b, and you'll get the same. And of course, using this notation. So this is nice, especially because we have a simple case of a two-dimensional system where we have an eigenvalue problem, essentially, right? So, okay, it's true. We have the eigenvalue problem where we have the vector alpha beta multiplied by the constant E1. And then we have the matrix W defined naturally with this notation with indexes A and B, multiplying the vector alpha beta. So this vector, if you remember, is basically the vector of the coefficients for the good states that we attempt to find, okay? So what this is telling us is that finding the correction to the eigenvalues and the good wave functions is equivalent in this two-dimensional degenerate subspace case to basically solve an eigenvalue problem and find the eigenvectors afterwards. And once we find the coefficients, and of course apply normalization condition, because in eigenvalue problems, the eigenspace, of course, is determined up to a constant, right? Because you can always multiply by a constant and it will still be an eigenvector. So the normalization condition at the end will be the one that completely determines the coefficients. But okay, in the 2D case, we can do directly this calculation. And so this is again a value problem in 2D for the matrix W. We'll get then the energy corrections to first order in the degenerate case. And again, eigenvectors will give us the coefficients for the unperturbed states. So this means that, of course, typically, as in any eigenvalue problem, that the matrix W minus E1 times the identity must be a singular matrix, which means that the determinant must be 0 for this singular matrix, if it's to be singular, actually. And then if you do the calculation, which in your head you can do by basically imagine that to this matrix we subtract the E1 identity matrix, which means that you'll have terms in minus E1 in the diagonal. And if you compute the characteristic polynomial, which is related to this determinant, you'll have WAA minus E1 times WBB minus E1, and then minus WBA and WAB. Now, okay, you can do that. You'll do the expansion of these terms where you have E1 squared minus the sum of the other terms plus WAA, WBB minus WAB, WBA. This actually, I mean, there's a very famous formula for the characteristic polynomial in 2x2 matrices, which is related to the trace and the determinant. So this is completely equivalent. And actually, after having done the full calculation, we can see you have 0 equal to E1 squared minus the trace of the matrix W, which is precisely trace is the sum of the elements in the diagonal, which is why you have WAA plus WBB, and then plus the determinant, which is precisely what we have here, right? WAA, WBB minus WAB, WBA. In fact, these are conjugates of each other because of the definition of W, but we'll go into that in a second. So anyways, regardless of the two formulas that you choose, you will calculate the energy corrections just by solving this quadratic equation. You can keep it expressing it in this way, which is, well, the solution of this quadratic equation is equal to the trace of w plus minus square root of trace of w squared minus 4 determinant of w divided by 2. And again, the trace is defined as the sum of the diagonal elements, which is why for 2 by 2 we have this case. The determinant, and again, this is where I stress, if you look at the definition of the W coefficients, we have WBA equal to psi 0b sandwiching H prime and then psi 0a, right? But that's the conjugate by definition of psi 0 H prime, then H prime psi 0b. This is because you have a Hermitian matrix, right? So you pass to one of the lines and then you invert inner product using conjugacy property, and then you have this. So because of that, when you multiply WBA by WAB, you have actually the norm of WAB squared because it's its conjugate. So yeah, if you go into detail, the determinant is WAA, WBB minus WAB, WBA. You use this, you get the conjugate over this part, basically, and then you'll have WAB times WAB conjugate is the norm of WAB squared. So you can use that. Going back to that expression, we could have used NF2, but we use this one just as a refresher of these properties of determinants in 2 by 2 matrices. So we have E1 plus minus, which are the two solutions to the quadratic equation, is a trace, which is WA plus WBB plus minus the square root of WA plus WBB squared minus 4, then the determinant that we just calculated over here. And again, we can do a small reduction or simplification of the terms, because if you expand, you'll notice that you'll get the double product of WA with WBB. And if you subtract the minus 4 WA WBB, you actually get WAA minus WBB squared, right? So you got it inside by expanding and combining with this, and then you'll have only plus 4 WAB squared. So this is actually neither. In fact, yeah, it's a neat expression. If you notice, the terms inside the square root are both non-negative. So that's nice. So that means, first of all, that these energies are real, as you would expect, because they're coming from a Hermitian matrix, etc. And yeah, I mean, these are the first order corrections to the energies. In fact, notice that you have a plus minus. So the only case where the degeneracy wouldn't be lifted is if the term inside the square root would be 0, because then E plus or E1 plus is equal to E1 minus. If, however, the term inside the square root is not 0, meaning that it's positive, then you will lift the degeneracy, right? So again, these are the first order corrections to the energies for the perturbed Hamiltonian case. And yeah, the common energy, which was E naught for the unperturbed case, splits into two different values because of these corrections. And of course, we're dealing with the degenerate time-independent perturbation theory, where we have to do things a little bit more careful. So what about the good linear combinations? I won't do the calculation here, but for the 2 by 2 case, it's clear what you have to do. I mean, this is an eigenvalue problem, so of course, finding the eigenvalues is only half of it. The other part, usually, as you might remember, is that you have to find the eigenvectors. So the eigenvectors in this case are basically the vector of coefficients alpha, beta. And you'll find a linear relation among the coefficients for the solutions. Then basically you have to use these coefficients back into the expression for the good states over here. But you have the condition that the norm of psi 0 should be 1. So from that, you will determine basically what are the values of alpha and beta, and you're done. So for a 2 by 2 matrix, the problem is not too complicated. I'm pretty sure that you have done that in either linear algebra, ordinary differential equations, or some other DFQ course of the sort, even possibly methods of mathematical physics. So I won't do that. I will just let you know what you have to do. I will show some examples though, so that hopefully is helpful. And yeah, you have to solve the eigenvectors. Now, that is one of the methods in which you can do it. And of course, for 2 by 2 matrices, it's simple. Maybe it will be more time consuming if you go to higher dimensions. And that's why we study a property even in this small 2-dimensional case, to possibly extend it to higher dimensional cases later on, which is an alternative way to find the good states. And so there's a theorem that we will use. So, okay, we either solve for the eigenvectors as we indicated above, basically, having found the E1 plus minus over here, or we use the following theorem. This theorem is useful especially when the problem has some symmetries that are obvious. Radial symmetry, symmetry under parity, etc., etc. Spherical symmetry. So the theorem goes as follows. Let's say that you have a Hermitian operator that commutes with H naught and with H prime. If psi 0a and psi 0b, which are the degenerate eigenfunctions of H naught, meaning they have the same energy for H naught, if these functions are also eigenfunctions of A with distinct eigenvalues nu different from mu, meaning that when you apply the operator A to psi 0a, it's equal to mu psi 0a. And when you apply it to psi 0b, you get nu psi 0b, where these eigenvalues are different by assumption. Then it follows that psi 0a and psi 0b are the good states to use in degenerate perturbation theory, and you can just use them. So, of course, I'm not saying that, I mean, it's not too complicated to find the eigenvector in this way, right? This is actually an elegant way to solve the problem, especially if the symmetry in the problem can be directly identified or it's natural, right? So just keep it in mind. Try to look at the Hamiltonians that you're dealing with. Notice if you can find some symmetry related to the problem. And if profitable, try to use the theorem in case you find the symmetry. Of course, the important part is, I mean, it's not even the theorem, it's finding the symmetry, right? Because usually the way you have an intuition into which operator A to use comes from identifying a symmetry of the problem, because then you'll find an operator that is Hermitian and that commutes with both of these. So more of that to come in a second. I'll start by talking about the proof. So let me drink some water. And so by assumption, since A is a Hermitian operator that commutes with H naught and H prime, it commutes with H naught plus lambda H prime. So you're just defining a function of lambda, which is H of lambda, which is the perturbed Hamiltonian with a given value of lambda. So it commutes with this by linearity. And so a property when you have a commutation is that you'll have common eigenfunctions. We're going to denote them by psi gamma of lambda, such that the following holds, meaning that, well, basically, it's an eigenfunction of the operator H, right? Which is the full perturbed Hamiltonian with a given value of lambda. So, well, because it's an eigenfunction of this, then it has eigenvalue E of lambda with this function. Now, it's also an eigenfunction of A, so that means that it has an eigenvalue that we're going to call gamma in this case. And so, well, we also know by assumption that A is Hermitian. So we're going to take inner product of this eigenvalue equation with respect to psi 0a. Sorry about that. And well, if we do that, okay, we start with this equation, right? Which is basically what we have over this part. So let's take inner product with psi 0a. So basically, if we do that, we take the eigenvalue gamma over here. We're just plugging in this part in here. So that's why the gamma is coming out. Then if we follow the calculation, what we're going to do is basically pass the A to the other side because it's Hermitian. And we remember, yeah, so basically we were here, we passed it to the other side, we have this, then we have this property, and because of that, you'll have mu psi 0a, and the mu comes out. Well, A is Hermitian, so the eigenvalues are real, so there is no conjugacy for the mu in this part. So this is nice. We get actually quite similar expressions, just that here we have gamma and here we have mu, right? So again, mu is equal to mu conjugate because A is Hermitian. So notice how we did it. We basically had this side of the equation over here. Then we use the Hermiticity property to pass to this side, and then use this property by assumption. And we got it. And so these are basically, well, multiplying the same term. So if you pass to the other side, you can factorize, and then you have gamma minus mu times this term equal to 0. So think that we have done this for any value of lambda, let's say in the interval 0, 1, right? So this holds independently of the value that we, lambda that we consider. So we consider in particular the limit as lambda goes to 0, right? And so, well, I mean, of course, we have lambda evaluated at 0. Um, and well, there are two possibilities, right, for this to be 0. Either this is 0, or basically this is 0, which would amount that gamma would be equal to mu. So we have the two cases, right? If we had done the same calculation but taken inner product with respect to psi 0b, we would arrive to something very similar. Basically, we would have psi 0b on this part. The process would be the same. You think about it, we would use this property, which would bring out the eigenvalue nu instead of mu, which would amount to this equivalent condition in this other case, which is, well, we would have something equal to 0. So either, well, one of the factors must be 0. So either this factor is 0, or gamma minus nu is equal to 0, which means that gamma should be equal to nu. And so, well, the good states are linear combinations of orthonormal states as below. And you cannot have the trivial solution of basically psi gamma of 0 equal to 0, which would mean basically if you restrict to these two cases, right? I mean, this will mean that the projection with all the elements of the basis is 0, and therefore the function is 0, or the vector in that eigenspace is 0. So one of these two conditions should happen. So that means that either gamma is equal to mu. If that is the case, basically, well, because nu is equal, or sorry, it's not equal to nu, so these two are different, that means that the other condition cannot hold because these were equal and nu are different. So that means that in this case, you should have psi 0 be equal to 0, which means that the coefficient beta by definition is 0 if you go back in the way the psi 0b is defined, just by taking inner product. And so that means that the good state is basically psi 0a. Or in the other case, if gamma is equal to nu, because we had one of these two possibilities, so that means that the inner product with respect to psi 0a should vanish, and that means that the alpha coefficient should be 0, since we have this expansion in terms of these spaces. And so the good state would be psi 0b. So this is proving the theorem. So these are the good states to be using. And again, why did we mention the theorem? Perhaps 2 by 2 calculation for eigenvectors is not so complicated. it will probably come in handy for higher dimensional spaces. But, well, the reason we mentioned the theorem in particular is that it's very useful when the problem has a symmetry. Because usually when, well, you have a symmetry, symmetries are associated with operators that commute with H. And this is the case where the theorem or the assumptions of the theorem apply, right? Where you would have A commuting with H, both the unperturbed and the perturbation with a given value of lambda. So you have two options. Either you identify the coefficients of the linear combination when the energies C1 plus are different, of course. So that, I mean, you need that because, well, if the energies are different, you have lifted the degeneracy, the eigenvalues are different, which will mean that the eigenvectors are different as well. And so the first order energy correction removes the degeneracy, and also you'll find linearly independent eigenvectors. So either you do that by solving the eigenvalue equation that we mentioned above, meaning finding the eigenvectors for the 2 by 2 matrix, or well, we use the theorem presented if you find the symmetry. And so in that case, we can identify the good states, and we can apply ordinary non-degenerate perturbation theory at the end. So the 2 by 2 case is very clear because you can calculate explicitly the also the eigenfunctions, especially if you go over this procedure, but particularly the eigenvalues. But, well, it's not hard to extend this to basically n-fold degeneracy, meaning that, well, you could have the general case of degenerate eigenspaces where the dimension of the degenerate subspace is either equal to 2 or greater than 2. So we can extend what we did for the dimension 2. And so we'll have to find the eigenvalues of an n by n matrix that we're going to call W, which will have the same notation. It's basically the matrix elements of the H prime in the basis that we chose for the degenerate subspace. So Wij is equal to inner product of psi 0 I times H prime psi 0 j. So yeah, it has the same notation. And if we find the eigenvalues of that n by n matrix, those eigenvalues would represent the first order corrections to the energy. Well, you will have the splitting in the perturbed case up to some degree. And the eigenvalue equation, of course, can be expressed in this simplified notation where we have the full matrix W. We have the vector of coefficients alpha, which is basically alpha 1, alpha 2 up to alpha n. And then, yeah, this is an eigenvalue equation because we have this matrix and we have the eigenvalue E1, which is what we want to find partially. And again, alpha is a vector of coefficients for the good states in the preselected basis that we have chosen for the degenerate subspace or eigenspace of dimension n. And then later on, the good states would be, as we did before, basically linear combinations of the basis of choice before. And sorry, got distracted by so many emails. Well, so it's simply the sum of the terms with respect to this basis with these coefficients that would come from the eigenvalue problem. And you can also try to use the theorem, excuse me, which is that if you can guess an operator A, again, by identifying symmetries of the problem, particularly of the Hamiltonians, commuting with H naught and H prime, then by using the simultaneous eigenfunctions of A and H naught from the problem, from the theorem that we proved a little bit above, it also holds in the n-dimensional case. In that case, you basically will have that the W matrix for H prime will be diagonal. And in that case, you wouldn't need to solve the characteristic equation. And so there are two moral of the stories for, well, actually one. It's just one. It's just expressed in different ways. A moral of the story for degenerate perturbation theory. The way Griffiths expressed it is that degenerate perturbation theory amounts to diagonalization of the degenerate part of the Hamiltonian. And the equivalent argument of McIntyre is, which is a good reference also for this topic. Actually, I encourage you to read both Griffiths and McIntyre in this case, in complement to these lecture notes. The moral of the story by McIntyre is that there is a mantra for degenerate perturbation theory, which is to diagonalize the perturbation Hamiltonian in the degenerate subspace, which is what you have to do. Nothing more. So, okay, this is the theory. We did it for two-dimensional degenerate subspace. Then we extended it for the n-dimensional case with n greater than 2. We can show two applications of degenerate perturbation theory. One second. No way I'm getting so many examples right now. So the first one is going to be a problem from Griffiths to show you how to use what we have learned right now. And it goes like this. Let's say that you have a particle of mass m that is free to move in a one-dimensional region of length L that closes on itself. And to fix ideas, we're going to think that it's a bead that slides frictionlessly on a circular wire. So you have basically circular motion, and the wire is of circumference L. This is just a reference to Griffith's problem. It's not important. I just put it in case you want to check on the book. And the first indication is the following. So show that the stationary states can be written in the form psi n exponential of I to pi nx divided by L. This is the argument of the exponential, complex exponential, and all these divided by square root of L, where the domain is minus L over 2 times L over 2. Of course, the domain should be restricted as we have this periodic circular motion. And the levels are n equal to 0, plus minus 1, plus minus 2, etc. And the allowed energies are En equal to 2 over m and pi h bar over L, this term squared. And so, okay, this is what we have to prove. You can kind of guess it from the periodicity of the problem. And what we will find in a second is that the only state that is not degenerate is the ground state. All the others have a degeneracy of dimension 2. So, okay, let's go to the solution, right? So, okay, the wave function representation in position space is called psi xt. Then, in this case, we have a free particle moving in a one-dimensional region. So the kinetic energy operator, which actually is going to be the full Hamiltonian, is, for the unperturbed case, is going to be the usual, right? Minus h squared divided by 2m times second partial derivative with respect to x. So that is because it's a free one dimension. If you want instantaneously along the tangent to the circle, I will talk about that in a second. And the Schrodinger equation that models this problem is the free particle problem, essentially, even if the motion is circular. The only thing is that you have to be careful about the domain where you are defining the problem. So you have a periodic condition, which means that because we're anticipating that the domain will, well, it's a circumference of length L, so the domain should be of length L. And for symmetry, we take minus L over 2, L over 2. And there should be a periodic condition, meaning that at the matching points, the wave function should have the same value by periodicity. So that is taking a charge of closing the curve on itself, okay? So you have a free particle problem. The periodic condition is closing the curve, and so you're back on track on the problem that you are intended. And so this is instantaneously a free particle along 1D with this kinetic energy operator as the Hamiltonian operator, where we are constraining the motion to be circular by means of the periodicity. So now we look for stationary states, right? So this is not complicated. It's basically like the free particle problem, or just having the Hamiltonian only made of kinetic energy. And if we look at the eigenvalue problem, basically we would have minus h bar squared over 2m second derivative of psi n equal to En of psi n. Okay, maybe I changed this. And so, well, passing terms, we have this. This is a second order ODE that you're very familiar with. You anticipate that you're going to get oscillating functions. which can be either sines and cosines, or you can choose a solution to complex exponentials. So anyways, this is what you would expect because you have circular motion, periodic conditions, so you have oscillations. This is nothing unexpected. In fact, you can guess it partially from the free particle problem. So if you solve the equation, you'll have that, okay, the general solution for psi n is a coefficient multiplying the exponential e to the plus minus I, square root of 2m en, then times x divided by h bar. So you have the plus minus because you have a second order ODE. Yeah, you can basically use the total derivative because psi n, since it's the eigenfunction, is only a function of x. So for a second order ODE, you have two possible solutions for the general solution case. We'll have to consider both. So just wait on that. And the eigenvalue, En, has to be determined from the periodic constraint, or will be determined from that. Actually, well, before we do that, we will find this coefficient by normalization because that's actually quite very easy to do. So we know that the norm of our wave function should be 1, or norm squared if you want. So if we calculate the norm squared, we would have the integral over the domain minus L over 2, L over 2 of psi n conjugate times psi n integrated over x. So if we plug in, we'll have the conjugate of the function times the function. That if you take the coefficients out, well, okay, you'll have the conjugate of this coefficient, which combined with the coefficient itself, you get the norm of the coefficient squared. The other thing is that over here you have the conjugate of this one. So here you have e plus minus, here e minus plus. And when you basically combine them, because of properties of the exponentials, you'll get 1. So this simplifies to 1. So you'll have a norm of a n squared, integral over the domain of dx times 1. So this is going to be L times a n squared, and this should be equal to 1. So that means that the norm of a n should be 1 over the square root of L. And okay, this is just a condition for the norm. So up to a phase, this coefficient should be 1 over L. So meaning that, okay, you can add a basically complex exponential factor that is just a phase, and it will still be valid. So just keep it in mind for the moment. But we might be able to select this if it is convenient to us. So we want to determine the eigenvalues. Again, we have a periodic constraint to be satisfied, which is that the value at minus L over 2 should be the same as the one on L over 2. And if you evaluate the exponential that you have in this case, and you don't care about the coefficient because it's going to be the same on either side that you take, basically what you'll have is e plus minus blah, 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 evaluated at minus L over 2, e plus minus blah, 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 evaluated at L over 2. You can pass this one to the other side, so you will add them, and then you have 1 equal to e to the plus minus I square root of this, L over h bar, right? So I just combine these two, or I pass this to the other side, and this is why I have 1, and here I have the double. So that means that, well, this being a complex exponential, of course, the energies are real, etc. And we have been careful to choose the energy level such that the En is not negative. So the options is that the only possibility by periodicity related to complex exponentials is that all these, including the h bar, of course, is basically 2 pi n for periodicity, with n either a natural number or 0, which is the star means that it's the natural numbers union 0. So, because usually natural numbers start at 1. So, okay, you can find some values over here. Basically, if you pass h bar to this side, you get this, then you take squares, so you'll have this squared, and then you pass it to m, which divides with the 4 that is coming in this part. So that's why En is equal to 2 over m, and pi h bar divided by L, all this is squared, with n basically 0, 1, 2, etc. So natural union 0. So this is what we kind of expected as before. Um, so we have more things to do though. So okay, we have found the coefficient up to a phase. We're going to stick with this choice. Um, yeah. So we have 1 over square root of L, exponential of this that we have found. So we plug in the value of En that we have, particularly of square root of 2m which we can find over here. So if we do that, the exponential that we get is this. And of course, I mean, it's clear that once you have this exponential, it will satisfy the periodic constraint because you have to evaluate basically at L over 2 or minus L over 2. So, okay, we have two solutions to our ODE or DFQ. So that's accounting for the second order. We can do a couple things. And this is actually not change in the solutions, it's just a change in the index notation. Because what we're doing here is that for each n, we have the plus minus. It only becomes a single solution for n equal to 0. For n greater or equal to 1, it amounts to two different solutions. But we can simply index over allowing the index to go to negative integers as indexes. So we can have for each integer n, we're going from minus infinity to infinity over the integers. So psi n equal to 1 over the square root of L, and then the sign is incorporated in the value of n. So this is just a different notation, but it's completely equivalent. Of course, the thing is that, I mean, in this notation and also in this one, uh, the plus and minus n had the same energy because you're squaring the n, right? So it doesn't change it, neither on this one nor on this one. So for a given n, especially let's stick to this notation, the eigenvalue will be 2 over m n pi h bar over L. Again, we have possibly negative n's, but you're squaring it, so it doesn't make a change. And in fact, this is showing especially that there is a degeneracy for n not 0, right? Because both psi n and psi minus n, where n is not 0, they are two different levels, yet they have the same energy. So this is what we wanted to prove in terms of the degeneracy. And of course, the only non-degenerate energy level is E naught equal to 0, right? Because first of all, okay, that corresponds to n equal to 0, but also because, well, it amounts to a single wave function. If you even go back to this notation, plus minus 0 is the same one. So you don't have two different or two wave functions, you only have one. So there is only one eigenstate, and in fact, I mean, what you'll have is exponential of 0, which is 1. So it's actually a constant. There's only one eigenstate, which is psi 0 for n equal to 0, which is 1 over the square root of L. So all other energy levels are doubly degenerate, meaning that they have two wave functions that are linearly independent, and that they have the same energy value. And yeah, En is equal to this squared with n greater than 0. And we have, for this energy level, we have two eigenstates with the same energy, right? Which is the plus minus n, just restricted to n greater than 0. So this is clearly showing that the energy levels for n equal or greater to 1 are degenerate. So, okay, so far so good. We have done what we were expected to. So, okay, the second part of the problem is, let's say we introduce a perturbation, right? And so the perturbation is going to be this, h prime equal to minus b naught, exponential of minus x squared divided by a squared. So this is a little bit like a Gaussian. And by assumption, we're going to think that the value of a is much smaller than L. So that is done because it's like a some sort of well-concentrated Gaussian. So again, it's like a little dimple in the potential, as if close to 0, you're making a perturbation to trap uh, the bead that is running along the circle. So that's why they think about it like a trap. So you have to find the first order corrections to the energies using the equation 7.33. And of course, keeping in mind that only the ground state is not degenerate. So you'll have to use your degenerate perturbation theory, especially two-dimensional, right? So there is a hint in Griffiths that we're going to use, which is that to evaluate the integrals, we're going to exploit the fact that A is much smaller than L to extend the limits from plus minus L over 2, which is the domain, to plus minus infinity. So this is an approximation. We'll justify it in a second. And basically they're saying, well, H prime is essentially 0 outside this interval. That is because this is a very well concentrated Gaussian where A is very small. So it's basically non-zero in that small region. And then outside you can kind of approximate that is 0. I mean, meaning that has very small values, the exponential decay is very fast, especially for a Gaussian. And so you can or think that you're having the same information if you integrate from plus minus L over 2 than integrating from plus minus infinity. So the solution, and clearly we can use two, mm, excuse me, two-dimensional degenerate perturbation theory. So the equation that they mention over here is this equation for the eigenvalues, which is what we have to use. So we have E plus minus, again, the trace plus minus, the square root of the diagonal terms being subtracted from each other plus for the norm squared of the off diagonal term divided by 2. And again, we're focusing on the degenerate subspace of dimension 2 for n greater or equal to 1. And so we'll have two indices AB. So we're focusing on the degenerate subspaces. So, I mean, if you want, you can do the calculation for n equal to 0 for the ground state. Since it's not degenerate, that's not the focus of this lecture, and you can do it for yourself. So let's remember the notation. Wij is equal to psi 0 I sandwiched with h prime psi 0 j, where the indexes are AB for ij. And if we plug in this Hamiltonian perturbation, the minus b naught will come out. And so we have the Gaussian sandwich by the unperturbed states. And we're going to do an identification because we're focusing, of course, on the each degenerate subspace. So meaning that for, let's think now in the old notation where n was going from 0, 1, 2, etc. And each value of n had two wave functions plus n and minus n. Okay, so basically the elements of the degenerate subspace, and actually that could generate a basis because they're linearly independent, are the state minus n and the state plus n. And so we are going to verify something, which is that the related eigenstates satisfy the condition. And I'm going to take the inner product of psi 0 minus n with psi 0 n. So it's the integral, then the square roots come out and they give 1 over L dx. And then if you think that you take the conjugate, basically this becomes psi 0 n, which multiplied with this one, it will be psi 0 n squared. That's why you have a 4 instead of a 2. And well, this is actually easy to integrate. We're in complex variables, but we can do the same kind of substitutions that you did in calculus, or basically the same integrals. So that's why you have the factor of in for pi. And then you have the exponential because integrated gives itself times some constants, and then evaluated at L over 2 minus L over 2. But the thing is, you have a periodic function. Basically, when you plug in plus minus L over 2, you'll basically have in 2 pi, and then this will die out, each one of the terms. So the good thing is that these are orthogonal, much in the same way that we assumed at the beginning of the lecture. So, well, let's calculate the states now, WAA, which, okay, if we go back to this expression, we'll always have a term of minus b naught. In fact, if you think about it, my psi minus n and my psi plus n have both a square root of L in the denominator. So if you take it out, it's a real term, you'll have the L dividing. And so we can focus on the rest of the wave functions, right, in this calculation. So you'll have a. So remember, a corresponds to minus n. So inner product of e to the minus in blah, 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 sandwiching the Gaussian exponential of minus x squared over a squared, and then exponential of minus in 2 pi blah, blah, blah. So if we do that, well, remember how inner products are defined, right? So of course you have the operator, which is over here, then the function, and this one is conjugated. That's why instead of a minus, you have a plus. Now, if you do that, basically there is some cancellation over here. So you'll have the plus minus this one, which will die out, and you'll only be getting the Gaussian, which is what you have at the end. So what you have, formally speaking, is minus b0 over L integral from over the domain minus L over 2 to L over 2 of the Gaussian, or proportional to Gaussian. So, well, this cancellation will also happen for WBB if you think about it. So you'll have the same terms, but now you have plus n inner product with the operator or the Gaussian e to the in. So you'll have, when you conjugate the minus, this dies out, and you have this. So for the diagonal terms of this matrix W, you'll have the exponential of minus x squared over a squared integrated over the original domain. So think about the hint that they gave you. On the other hand, if you consider the off-diagonal terms, basically, okay, you have again this old coefficient, our old friend, you have the minus, here you have the plus, and then the Gaussian, right? But the thing is, when you take the inner product, etc., you have to conjugate this one. So you'll have the plus, which adds with this plus over here. So this term won't disappear. Actually, what you have to do is to combine them, and to combine them also with the Gaussian. So now you have an exponential, which is made of basically a real part and an imaginary part in its argument. Okay, that's why you have doubly this, in for pi x over L, and then minus x squared over a squared. So I'm using properties of the exponential. And again, the domain of integration is the bounded one. So likewise, for the other off-diagonal terms, a similar story will happen. You have plus here, minus here. When you take inner product, you have to conjugate, so you get minus. So you have doubly the minus combined with this one. So that's why you have integral times this constant of the exponential minus in 4 pi minus x squared over a squared. Okay, so for the off-diagonal, basically the complex part does not disappear. For the diagonal terms, it does. Nevertheless, it's very clear why they gave you this other hint of like, well, the Gaussian is here outside the domain, absolute value of x less or equal to a. So I just take the integrals over plus minus infinity anyways, because, well, I mean, this is equivalent to basically saying that a Gaussian has most of its probability very concentrated in some standard deviations. But again, the approximation indicated in the hint is that to evaluate the integrals, a is very small with respect to L. And so because most of the non-negligible part of this integral is concentrated in this region, it means that outside of it is mostly zero, or it's a very negligible small part. So it doesn't make a difference if instead of computing this, you compute it over the limits of integration minus infinity plus infinity instead of the bounded domain. And they do that because we have easier formulas for this case and for this case when the limits of integration are plus minus infinity. That's the whole reason, right? So I gave you a justification, meaning, well, related to the non-negligible part of the Gaussian inside of this domain anyway. So what's the difference if we take just the limits of integration to plus minus infinity? And again, the argument is that h prime, this Gaussian times minus b0, of course, I'm saying proportional to Gaussian, so Gaussian is very loosely. I'll be more precise in a sec. So this is very small outside this interval, minus a to a. So again, h prime is proportional. It's not equal, but it's proportional to a sharp Gaussian that is concentrated, most of it, not all, but most of it, on the region absolute value of x less than a, because a is very small with respect to a. So once you go outside that region, it decays very quickly to zero. And then if you take the limits of integration, it will make little difference as we will be adding a very small quantity. So under this approximation, let's do it, right? So, okay, this is the exact value. The approximate value is just changing the limits of integration, and this becomes more recognizable. This is basically proportional to the integral of a Gaussian. This is a Gaussian, but multiplied by a complex exponential, so you might have to think of decomposing this into sines and cosines, and likewise here you have the Gaussian. So, I mean, these integrals are usually seen in a course of methods of mathematical physics. Um, I'm gonna use that knowledge if you want to verify them. So either you can find them on a table of integrals or in a basically symbolical computing software such as Mathematica, Maple, Wolfram Alpha, your software of choice. And for the Gaussian, you have this property. Basically, that's the normalization coefficient of the Gaussian, actually. So the integral of from minus infinity to plus infinity of e to the minus x squared divided by x squared is equal to square root of pi times a squared. And likewise, no, this is actually a small trick that we do for the other. Because, okay, here you have a complex exponential, so it might seem more complicated. In a way it is, but what you have to do is to decompose into cosine and sine. So exponential, complex exponential is cosine of the argument plus minus I sine, the plus minus because you have the plus minus over here, times the exponential. And so there is one that is very easy to show that it's zero. And it's, well, and it's the imaginary part, because this will have a real part and an imaginary part. However, the imaginary part is zero because you're multiplying an even function with an odd function over the integral or interval minus infinity to infinity. So it dies out just by symmetry considerations. On the other hand, this other has to be calculated. So if you basically were to calculate the integral from minus infinity to plus infinity of this cosine times this exponential, you would have this result. So square root of pi a squared times this exponential and plus minus I zero. So I, for clarity, indicate that the real part dies out, just to compare. So, well, I mean, I could have basically written just equal to cosine because the other dies out instead of the exponential, and then write the full result. So again, the imaginary part dies due to integration of an odd function over the real line. But okay, this one was expected. It's approximated by the formula by the Gaussian by taking the limits of integration to infinity. In the other, I'm using this result, so I'm plugging it in already. And WBB is also related to the Gaussian, so it has the same value. So we have now the coefficients of the matrix that we need in order to calculate the energy corrections up to first order. So E1 plus minus is again the trace plus minus the square root of this object. I'm simply going to plug in the coefficients. I'm actually going to get some reduction, which is nice. So this is the sum of the diagonal terms, right? So which are the same. So divided by 2, they will give me the same. So this one was easy. Then I go plus minus. Think about it. The diagonal terms are the same. So this is 0. Okay, so I don't care about it. Now, I just have a square root of 4. So the thing is that the 4 will come out of the square root and you'll have 2. So that will balance with this factor of 2. Then you will have a square root of this squared. So it's actually only the norm. So you only need the norm of, say, the off-diagonal terms, which are actually the same because the imaginary part died out. So there's no difference. So again, there is a balance, and I just need to put the absolute value of WAB times the plus minus, of course. So if I take absolute value, this minus goes out, which is why I don't put it here. Then I have B naught over L. This is positive because it's a square root. The exponentials are never negative. So basically, I just put the same. So the only effect of having this absolute value was to take out this. So it doesn't appear. And well, you have a common factor actually over here. So if you factorize, especially with the minus, you'll flip this sign. So that's why you have a minus plus instead of plus minus over here. But otherwise, you have this coefficient with the minus multiplying 1 minus plus because we flipped the signs, and then exponential of this stuff. Now, I mean, we have made an approximation, but it's comforting to notice that actually the correction to first order is not zero. Why is that? Well, because the only way this could be zero is if basically this would be zero, right? If you, well, you had, say, e to the zero, but that's not the case. So because this is a non, well, this term is not one, uh, you will have one plus minus term different to one. And okay, one will be adding, the other will be subtracting. But anyways, the terms are different. First of all, they are not zero. Second of all, they are different because they are plus minus non-zero term. So the degeneracy has been lifted up to the approximations we have made. And especially, not only this is not zero, but E1 minus is different to E1 plus. So, okay, that is nice. Up to the approximation, because of course, we approximated the integrals by taking the limits to plus minus infinity, but okay, that was part of the hint, etc., etc. So, okay, what are the good linear combinations of, so this is a different part of the exercise, of psi n and psi minus n for this problem? Okay, let's think about it, right? And they also give you a hint, which is use a given equation and show that with these states you get the first order correction using equation 7.9. Okay, the solution goes as follows. So we, to find the good states, we need to solve the eigenvalue problem. Um, we can do it in two ways. In fact, D will be part D, which is the next part of this full exercise, will be done by identifying a symmetry operator. In this case, we're going to do the eigenvalue solution. So we only need to find the eigenvectors for this two-dimensional problem. So basically, we will work with a 2 by 2 matrix. And then again, later we'll completely define the coefficients by normalization. So the eigenvalue problem that we have, of course, we have passed the the energy times identity matrix to the other side. So that's why we have the diagonal terms being subtracted by minus E1 plus minus. So this is the equation to find the eigenvectors, since we already know the eigenvalues over here, approximately. And if we plug in, we plug in the values of WAA, WAB, WBA, WBB that we found over here, which is what we have, right? And so, actually, if we take difference with respect to these terms, we'll have to do it. So some terms will die out. So, but okay, those are the diagonal terms of this matrix. And for WAB and WBA, we have these formulas. They are the same, it's just this term. So we just put it in here, okay? Now, if we substitute for E1 plus minus, we'll put the full term. So this has a minus. With the minus, it becomes a plus. Now we see that some cancellation will happen, which is nice, always nice. And so, okay, these are the off-diagonal terms. For the diagonal terms, we just need to subtract this part, which actually will kill this term. And you are only with this part times this coefficient. So that's why you have this coefficient multiplying plus minus this, then the off-diagonal terms, and then this coefficient multiplying the minus plus part. Sorry about that. So, well, actually, it's quite nice that most of these have the same factor. If you notice, it's basically b0 square root of pi a squared divided by L, and then the exponentially decaying thing. So the only thing is that, well, in this one, the sign is defined, and the other you have a minus plus. In fact, if you basically multiply this matrix by a minus, these become positive because it should be equal to zero. So what's the difference to with respect to multiplying by a minus? So this will become plus minus, and then you factorize. I mean, basically, that means that actually the matrix times the alpha beta should be zero, where you can take out the coefficient, you divide by it, you divide by zero, so it doesn't make any difference. Sorry, you divide zero by this coefficient, and then you have plus minus 1, 1, 1, plus minus 1. So you just divide it by the common factors that all these terms have, and you have this simplified equation for alpha beta. So this is actually quite nice. And I mean, this is the typical way an eigenvalue problem usually appears for, yeah, when the case is very simple, very nice. The values of the coefficients are not different. So there is one case, right? So the case related to E1 plus, which is related to the plus sign. So it's alpha plus beta equal to 0, which actually gives you the same equation no matter where you go. That's also very typical of eigenvalue problems or eigenvector problems. So that means that alpha is equal to minus beta. And so the vector alpha beta of coefficients is having a common factor beta and then minus 1, 1. Now, what about the negative case, right? E1 minus. So we'll have to use the minus here. So that means minus alpha plus beta equal to 0. The other one is the same equation, just multiplied by a minus sign. So that means that beta is equal to alpha in both cases. And that means that alpha beta is a beta coefficient multiplying 1, 1. So this is actually giving you the directions of the eigenvectors in these two cases, right? In one of them basically goes along the line uh, x equal to y, and the other x equal to minus y. Mm, But okay, now you have found the good states for these two different cases, right? So using this index notation of the plus minus, so basically the good states, psi 0 plus minus, of course, the plus corresponding to E1 plus, the minus corresponding to E1 minus, is basically if you factorize with the beta, it's basically phi 0 n minus plus psi 0 minus n, just from what it in here. Just think that basically alpha is the minus plus in these cases, right? Because for the plus case, it was minus with respect to beta. For the minus case, it was plus with respect to beta. So that's why we have this expression. You can do it. Now, from normalization, yeah, I mean, we have this coefficient, which is what ultimately defines the value of the coefficients. I'm pretty sure that you have done a calculation like this before for two-dimensional problems because these some sort of entangled states come to appear quite often. And so you have 1 equal to the norm squared of this element, which is inner product with itself. So the beta factor comes out, and then you have plugging in all these. That's why the beta squared normalized, of course, comes out. And then you have this inner product with this, which is itself. And you can do some sort of inner product decomposition by linearity. Doesn't matter too much. Of course, the terms that are relating different states will die out. So basically, um, the plus minus terms, because they're combining minus n with n, will die out. The ones that survive are the, well, when the state is multiplied by itself. So this is beta squared 1 plus 1. So this is 2 beta squared, and that should be equal to 1. So basically, you have norm of beta equal to 1 over square root of 2. So by this point, you can figure out the form of the state that we should have. Basically, we have, well, psi 0 plus minus. We have, let's, I mean, up to a phase. Yeah, this is important to just keep insisting on. Psi 0 plus minus. And I would like to actually clarify, since not beta. Okay, since beta is equal to this up to a phase, we have the condition for the norm, but okay, let's take it just like that, right? So we plug in the beta like that, and then psi 0 n plus minus psi 0 minus n divided by square root of 2 coming from the beta coefficient. If we plug in that, and then, yeah, I think you're anticipating what we were going to get. First of all, this is nice. This is the usual form for this, kind of like entangled states. Secondly, we have the e to the in, blah, 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 minus plus e to the minus n. So this is actually some sorts of combinations that you have seen before in your complex analysis class. So psi 0 plus, meaning that we take basically the minus sign in this case, because this is plus minus. So this will actually give you the I sign, right? So, well, I mean, you might be wary of why the imaginary thing came out, but remember that we chose beta up to a phase. So we can make the choice later, or the change of choice, um, you know? So in any case, they're proportional, and this will also be an eigenfunction provided that you multiply by a non-zero complex constant. So, well, when you have this, you basically have 2i, um, the real part, that's why the sign is coming out, and then the resultant division, uh, that's why you get the 2 in the numerator instead of the denominator. The simplest case, of course, might be psi0 minus, which has the plus sign in here. So ein blah 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 plus e minus in blah blah blah. So this will just keep the real part twice, which is why if you divide, well, so factor of 2, which becomes in the square root of 2 by performing this operation. And then you have twice the real part, okay. So that's why the cosine is coming. So yeah, I mean, this is in a way equivalent to say that complex exponentials can be represented by sines and cosines. The important thing is that these are the good states. We have found them by solving the eigenvector problem, right? So, and again, we remember that the coefficients beta plus minus are defined up to a phase. Um, yeah, I mean, this is notation. It doesn't make a difference. So we can simply multiply by an I, for example, or a minus I if you want. Or we can take the imaginary number out. And so the good states, just because we want it as real valued functions, psi 0 plus equal to square root of 2 over L, multiplying the sign of n2 pi x over L, and then psi 0 minus equal to square root of 2 over L cosine of n2 pi x over L. So, well, um, yeah. So the different thing, yeah, because this was an indication in the exercise, right? I think. Show that with these states you get the first order correction using equation 7.9. If you wonder what was equation 7.9 in the Griffiths, it's actually the equation of the first order correction to the energies in the non-degenerate case. You can check it on your Griffiths book. Yeah, I just included for reference. So this is just a sanity check for this exercise. Let's do that, right? So we just want to verify that we get the first order correction equal to this. So we have already calculated which are the first order corrections. You just have to, well, so the first order corrections were calculated here. If you don't remember, we just have to basically show that for this example, they're equal to this. And this is coming from plugging in the H prime perturbation. So we will have to use, of course, the same approximation as before. I mean, first of all, for consistency, because you cannot use the approximation in one part and just not in the other, but also for simplicity. And so using the same approximation as before, um, we'll have minus b naught, okay, psi 0 plus exponential of minus x squared over a squared, psi 0 plus. So again, I mean, the formula for non-degenerate is using the unperturbed states, and of course the same, so that's why we have plus plus. If we plug that in, and yeah, let's do that, right? So okay, these are real functions, so the conjugacy won't make a difference. In fact, well, the factor 2 over L squared, well, square root squared, so that's why you have 2 over L, we come out, because you're multiplying these two. And then you'll have sine squared of this, and then you'll have the Gaussian, and then times the x, right? So, okay, what to do here? This looks a little bit complicated, but actually, if you use your trig identities of the sine or the cosine of the sum of two angles, etc., you can show that sine squared of this is 1/2 of 1 minus cosine of the double of the angle. Yeah, you should remember, actually, I must mention that in quantum mechanics, these sorts of integrals come very often. So I'm pretty sure that you have realized that in your previous course. And if not, I just encourage you to remember these trig identity properties of the cosine of the sum of two angles, etc. So we're justifying that by using a trig identity over here. And we're doing that because, well, I mean, it might be simpler just to use this function instead of the sine squared. So the first one, since now we have this, we multiply
The first one is going to mount by a Gaussian, right? In fact, I'm also using the same argument that, well, this is some sort of, well, it's not exactly a characteristic function, but it's going to kill outside its domain. And so it doesn't make a difference, especially because A is very small compared to L, that instead of like thinking about the limits of integration as plus minus L over 2, we just take plus minus infinity. So what's the difference? So if we do that, well, we'll decompose actually this in two parts. And so now you see why you get the equality, because this part is corresponding to the Gaussian integral that we did over plus infinity minus infinity. And this other was actually the real part of the complex exponential that we performed. If you go back to, and I want to go back just to show clearly, let's go back to this one, right? We had this complex exponential. We divided in a real part and an imaginary part. And we stuck with the real part because the imaginary died out. But this is exactly the same. So we're going to use the same formula and actually retrieve the second coefficients that we found in a different way. So if we do that, basically we have the sum of the two integrals that we had last time. And so we can factorize, actually, minus b0l, square root of pi a squared, all that over square root. And then you have 1 plus e to the minus this thing. And if you go back to the formula, that's actually e1 minus. So, I mean, let me go back to this one because this is where I started. Sorry about it. So basically, here what you did is use trig identity, multiply by the exponential, recognizing that you had the same integrals that you had before. In this case, you have a minus sign, so that's why you have this. But still, you have some common factors, especially the square root, that you factorize. Then you have all this times 1 minus this exponential, which is exactly equal than e1 plus that we obtained before. And if you do the same calculation, but for the state psi 0 minus, basically see where the plus comes instead of the minus in this case. I mean, the minus came from this trig identity. So if we were to do the same, well, here, the psi 0 minus, of course, is a cosine. So you'll have the cosine squared. So you use your trig identities. And then for the trig identities, you have that cosine squared of this is 1/2 of 1 plus cosine of twice the angle. So now you have the plus instead of the minus, as in the case for sine squared. So because you have this plus, basically, again, you'll first of all extend the limits of integration on the argument that the Gaussian is very concentrated on a very small region. So that's why you take the limits of integration to plus minus infinity. Then you multiply. You have two integrals that you remember for which you had the formula. So this is square root of pi a squared. This is the other one that we found. We factorize this square root factor. And then you have minus b0 over L, the square root of this, 1 plus exponential of this stuff. That was actually E1 minus. So yeah, first of all, we're getting the energy correction. Second of all, we're getting them in the right wave function, right? So the plus with the plus, the minus with the minus. So our good states, yeah, we get indeed the first order correction formula for the energy. So that was for Degenerate perturbation theory. So this is part of the exercise. And then the interesting part, which might be a little bit new, in addition to the degeneracy, but also in this thinking about symmetries, is that you have to find a Hermitian operator that fits the requirement of the theorem. And basically that commutes with both H naught and H prime, right? And show that the simultaneous eigenstates of H naught and A are precisely the ones you used in C. So this is actually a very interesting problem. You have to think about it for a second. Because, well, you might be worried like, well, you know, um, I'm so sorry, I got an email. Oh, sorry. I'm sorry about the distraction. Um, yeah, sorry about that. Well, so you want to find a Hermitian operator A that commutes with the perturbed Hamiltonian, which is only a kinetic energy operator and made basically of momentum operators. and with H prime, which is this Gaussian perturbation, but that depends on x squared, if you think about it. Now, I mean, okay, I'll have to give you the solution right away, but the important thing to notice is that H prime, the perturbation, is a function that has even symmetry with respect to x, because since it depends on x squared, it doesn't matter if you use plus x or minus x. So that is interesting because you have a function with even symmetry. Um, why am I emphasizing this? Well, because if you just think of these two operators without that property, it might be a little bit hard to find the operator that commutes. But okay, your intuition will be like, well, this Hamiltonian perturbation has even symmetry. What if, because it has even symmetry, we use the parity operator as the proposed operator for A? So the parity operator, as you may remember, is the operator that acts on functions in this way. If the parity operator P acts on f of x, then it becomes f evaluated as minus x. That's the definition of the parity operator, and most probably you saw it on last semester. So let's say that you were to use this one, right? What about the commutations? And so we're going to check the value of the commutator by basically evaluating on a function, which is going to be psi of x, right? So, okay, by definition, we of the commutator, we have um, commutator of p and h naught, p evaluated over h naught of psi of x minus h naught evaluated of parity operator evaluated at psi of x. So, okay, on this one, you have to basically change the sign at the very end. And here you have the kinetic energy operator, right? Second derivative, constants, etc. And then you have minus h naught. So minus minus becomes a plus. That's why you have this. Then partial squared with respect to x. So this is coming at the very end, evaluated at psi of minus x. And this is actually 0. The second one is basically the commutator of p with h prime, evaluated a function psi. So psi doesn't need to be a wave function, by the way. I mean, it just, I could have written f if that makes it clearer, but never mind. It's just important which effect it has on the function just by these two operators. So this is p of h prime of psi minus h prime of p of psi. So in the first one, you have to change the sign at the very end, and then you have minus b naught exponential of minus x squared over a squared psi. On the other, you have, okay, the minus sign goes out because you have the minus h prime. So this is the potential, and then multiplying parity operator applied to psi of x, so psi of minus x. Now, here's the thing. Here, because the Hamiltonian perturbation is an even function, okay, psi will change sign, but this part won't, because you're taking minus x squared, so that's the same as x squared. Later on, you multiply by a minus, but that won't make a difference, so you get actually this term. Same situation happens under this case. So actually, both commutators are 0, and this parity operator is satisfying one of the requirements of the theorem. We need to prove some others. The second condition was that the operator was Hermitian. Is it? You probably saw this in the previous course, but if you haven't, let's do it just for sanity check to verify. So we can do actually the calculation in two different ways. One in the position basis, so basically P of x and y, which is a matrix, but it's a continuous matrix if you want to think about it this way. So inner product of y with P of x is minus x, so the minus comes out. Then you use inner product properties, minus xy conjugate. Then you put the minus inside because that is related to minus 1. It's conjugated itself because it's a real constant. Then you basically have x applied of parity operator to y, and then this conjugate hasn't gone, and this is exactly parity operator xy, I mean in this matrix representation of continuous states, conjugated. So this is what we wanted to property. If you want an equivalent proof, if you don't feel comfortable using the position basis, we can do it. And notice that I didn't even have to compute anything over here. I just had to use properties of inner products and I was done. So here, okay, I'll have to slightly compute some things. Many things will die out actually. And so PNM is inner product of psi n, parity applied to psi m. So basically, okay, I have the conjugacy over here, and then parity of this, that's why I apply minus x. Now, I will use the old trick of basically conjugate of conjugate is the same. So that's why basically I'm reserving the conjugacy over here. Then the other psi conjugate conjugate for m is giving me psi m, so I have the same thing. I haven't changed the minus. I will simply change a little bit the order of things. Um, well, actually, wait a second. This is the same, so this isn't necessary. Okay. So, well, yeah, okay. And maybe I wrote, sometimes I copy paste things and they appear 3 times. Yeah, so what I did over here is, okay, so far so good. We did a change of variables, passing from this side to this side, where basically I define a variable y, which is minus x. So that's why I have basically x minus y, and then minus x is equal to y. Then this is differential of minus y, and then I have flipped the order of integration. So the effect of this minus is to basically bring back the good order of integration for this part. And then I'll have reordering things, just putting this on the other side under the new variable, psi m star of y, and then psi n of minus y, all these integral conjugated. And so if you recognize, basically, I mean, I'm having a dummy variable because I'm integrating over y, so it doesn't make a difference if I use the x or the y here, but it's actually the same thing, just conjugated. And so that's why I have, well, same thing in a similar expression. Sorry about the loose speaking. So this is basically, if you recognize by using this variable, this is psi m inner product with parity operator applied to psi n. And then this is conjugated. So you have the properties in this case. So actually, yeah, the parity operator is a good choice for what we want to do. It's Hermitian. It commutes with both h naught and h prime. So that's nice with the unperturbed and the perturbation. And so that is all what is needed. Now, what are the eigenstates of the parity operator? And this you probably saw, but if you haven't, you can have an intuition into what are the eigenstates. Are basically functions that are symmetric or anti-symmetric, meaning that either they have odd symmetry, which means eigenvalue minus 1. Just think about this, right? If you were anti-symmetric, f of minus x is equal to minus f of x. So the eigenvalue would be minus 1. And if you have an even function, it's even easier because even symmetry means that f of x is equal to f of minus x. So that means that the eigenvalue would be plus 1. Now, the important thing is that these functions of either odd or even symmetry, they should be defined in our domain, which goes from minus L over 2 to L over 2. It is bounded, but implicitly, we require a periodic condition, psi of minus L over 2 equal to psi of L over 2. And this is exactly the same condition that we applied in our previous subsection of the problem. So we're going to require it for the parity operator too. What does this requirement mean? This means that we need to find odd or even functions which have period L, because they must be periodic in this case. And not even that, but actually, I mean, the fact that they have to be periodic, it restricts the functions to be represented by a Fourier series. This is kind of like and we are arriving at this from a very different condition. We're just basically saying, okay, give me all the functions that are even or odd, but that have to be periodic with a periodicity L. And basically you think, well, okay, they have to be periodic. That automatically restricts that because they have a period L, they can only be represented by a Fourier series. So, I mean, they can have many forms, etc., but they must have a Fourier representation because they are periodic. You have that knowledge from ODEs, differential equations of second order, etc., but you know it.
So that's only because the functions are periodic. So far, we haven't used the parity, but it's a very important constraint. And so we're saving a lot of work by using this mathematical property. So we are being somehow elegant in the way we are thinking about this, because by imposing the condition, we go directly to the solution that we have to achieve. So basically, we need to find odd or even functions which have period L. The fact that the periodicity needs to be of period L, it restricts the functions to be represented by the following Fourier series. And in fact, I mean, if you have even functions, they have to be represented by a Fourier cosine series. And if you have odd functions, they have to be represented by a Fourier sine series. If you have not seen what a Fourier cosine series is, it is this, meaning that, I mean, you can only use cosine functions in the representation because this is an even function. And if you need to have a Fourier representation of an odd function, it has to be only by means of sine functions. That is, and now we're actually using the parity operator in a way. We're restricting the symmetries that the eigenfunctions of the parity operator must have, either even or odd. And so this comes out with the previous combination of Fourier representation due to periodicity to using only cosine or only sine. And now, even and odd functions are, of course, eigenfunctions of the parity operator with eigenvalue plus minus one. This, if I was hand wavy a little bit ago, um, is what I meant. So parity operator of a function either even or odd, function evaluated at minus x, and then plus minus depending on the symmetry. And this we know that holds for cosine and sine because, I mean, it's clear. Cosine is an even function and sine is an odd function. So they also have this property. And that's why we're using them as the basis. And actually, from the Fourier series above, it's clear that the cosines, where n is allowed to be zero, because then you would have a constant function, this is an orthogonal basis for even functions. I'm saying orthogonal because they are not normalized yet. And then the sequence of, or the set of sine functions of this form, where n goes from 1 to infinity, to avoid the zero case or the trivial zero case for n equal to 0, is orthogonal for odd functions. So this is clear from this part because basically I'm able to represent any even or odd function that has to be periodic with period L in this fashion. So if we impose a normalization condition, meaning that we have to normalize each one of these functions, which is actually the same calculation that we did above, because the eigenstates that we got before as the good states were basically proportional to this. If we impose a normalization condition, then the orthonormal eigenbasis to the parity operator has this factor of a square root of 2 over L that we calculated before. I'm not going to do the calculation again because we did it. But the whole basis for eigenfunctions of the parity operator, it's basically represented by the union of these two sets. So this is related to the basis for even functions. This is for odd functions. And so these are therefore simultaneous eigenstates of A equal to P and H naught, as they are precisely the ones we obtained in C. So basically, once you arrive to this and you say, oh, actually, this is my basis. Oh, but if I normalize it, I get this. Well, these were actually exactly the same states that I got for the good states. So, I mean, this is a very powerful argument. Actually, if you want to skim over the method for solving this subsection, which actually is quite nice, is first of all, recognizing a symmetry of the perturbation Hamiltonian. In this case, it had an even symmetry. So because you have even symmetry, you think of using the parity operator. You verify the commutation properties. Then you verify that it's Hermitian. Once you do that, you go back to your problem. And then you realize, okay, there is another condition, which means that the function should be periodic of period L. That is a very big step. And it's very elegant because that way you say, oh, well, then these periodic functions must have a Fourier representation. And actually, if they are even, they must have a cosine Fourier representation. If they are odd, they have a Fourier sine representation. You have to keep them separate because if not, you basically screw the symmetry. Okay. Um,
So basically, yeah, the orthonormal eigenbasis related to the Parity operator is the union of these sets, one of them representing even functions, the other representing odd functions. And you have found a nice operator that equivalently arrives to the good states. Of course, using very strongly the condition of the um, functions needing to be periodic. But think about it. I think this is a nice problem because it analyzes in detail the stuff for degenerate states for 2D degenerate states that we performed. In fact, you have to do the calculation twice. One, just by solving this 2 by 2 matrix eigenvalue eigenvector problem, and on the other, elegantly finding this uh, operator that commutes with basically the Hamiltonian on and perturb, and then using this operator to find the good states, which the condition to be periodic helped us a lot to arrive very quickly. So think about it. I think this is a very nice problem. I'm going to stop here for this part. I'll continue with the final part of the generate subspaces of a higher dimension by presenting a physics example, which is the hydrogen atom and the Stark effect. But for the moment, I think this is enough material to digest. So I will upload the video today, Monday, and on another day of the week, I will put the rest of this degenerate subspace of dimension n and the time-independent perturbation theory as an iterative method, so that by this week, we will have finished the time-independent perturbation theory topic. But for the moment, I hope the example presented is helpful to have a first look at degenerate perturbation theory. Let me know if you have any question. I'll have office hours. And well, have a good week.